All right, let's remind ourselves what a limit is. In problem 77, it wants to know, for what value does the limit as x approaches a equal 0? Well, for a limit to exist, as you approach a value from the left-hand side and the right-hand side, they have to meet at the same coordinate. So if I approach 2 from the left and the right, do you agree that they both meet at 0? So I think 2 is a good answer. If I approach 4 from the right and the left, do you agree that they also both approach 0? Now, here's my reminder about limits. Limits don't matter what happens at the point. They don't care that there is a removable discontinuity or that this is a point discontinuity. They don't care. Limits are where as I approach 4 from the right and as I approach 4 from the left, do my fingers come together, if you will, at 0, and it's true. It's not asking what is the value of the function at 4. It's saying, does the limit at 4 equal 0? And I'd say, yes, it does. So I feel good about 2 and 4, and I guess that's going to narrow my answer to B. Let's talk about why it's not 0. As I approach 0 from the left, the value of my function is 0. As I approach 0 from the right, the value of my function is -1. Therefore, the limit does not exist at 0. And if I were to take a peek at 1, as I approach 1 from the right versus 1 from the left, they both come together at -1, and they wanted the limit to be 0. Okay, problem 5. It says, which of the following is true? And 5 is saying, as I approach 2 from the left, the answer is -1. The limit is my fault. As I approach, f of 2, so I'm going to erase because I've kind of drawn on this. F of 2 is the value of the function when x is 2, which is also -1. So I like option A. In option 2, it says the limit as I approach 6 from the left equals the limit as I approach 6 from the right. Again, as I approach 6 from the left and 6 from the right, they're both approaching -1. I don't care that the function at 6 is not -1, but the limit is. So I like 2. In 3, it's saying the limit at 6, and again, because the right and the left, the limit at 6 is -1. Is that equal to the value of the function at 6? And the value of the function at 6 is actually -3. 1 does not equal -3, so I do not like option 3. I like C. The next question says, which of the following statements is true? All right, is the value of the function at A 2? False. The value of the function at A is 1. So I do not like A. And then it says, is my function continuous at A? False. I've got a point discontinuity or removable discontinuity. Option C says f of A, the limit as x approaches A is 1. Well, as x is approaching A, correct me if I'm wrong, my limit's looking like 2, not 1. So that's making me like D. And E is wrong because it says the limit does not exist. And here's what I am to tell you. The limit as x approaches A does exist, and it is going to be 2. All right, in order for a function to be continuous, the value of the function at the point 1 has to be equal to one another. So I'm going to set 6 plus cx equal to 9 plus 2 times the natural log of x. They want to know, is it continuous at 1? So I'm going to go ahead and plug in 1 for my x. Oops. And that's equal to 9 plus 2 natural log of 1. We know that natural log of 1 is 0, so this is gone. We would have 6 plus c equals 9. Therefore, my c has to be equal to 3. On 10, it says, for what value of b would my function be continuous at 2? Well, before we go setting the top equation equal to the bottom equation, like we did on the previous problem, what I notice in this is that if my x is 2, regardless of what b is, 2 minus 2 is 0. I'd have a 0 in denominator, therefore my function is going to be undefined. So it cannot be continuous at 2 regardless of what b is, because when I plug in a 2 here, I'd get a function over 0, and again, that'd be undefined. So this question, we're going to save some time. There is no such value of b for my function to be continuous at 2. Let's remind ourselves the different types of discontinuity. At 3, we have point discontinuity or removable discontinuity. We have the same thing at 10, but when x is 7, that's where we have a jump discontinuity. They also put 1 as an option because my function is not differentiable at 1 because of the cusp per corner. It's also not differentiable at 3, 7, or 10, but I think that's where they put the 1 came from. Okay, for my function to be continuous at 2, again, we are going to set the top function equal to the bottom function. So I've got x squared times the sine of pi x. It's got to equal x squared plus cx minus 18. When x is 2, I'm going to make a substitution. So I'd have 4 times the sine of 2 pi. It's going to equal 4 plus 2c minus 18. And they said we got to solve for c. Well, the sine at 2 pi, the unit circle is 0. So I'd have 0 equals negative 14 plus 2c. Move my 14 over and I'll get c is 7. On 23, they want to know what is the derivative of my function at negative 1. Where we're going to get caught is we're going to want to say, well, my function exists at negative 1 on the bottom function. So a lot of people are going to only want to find the derivative of the bottom function and plug in negative 1, which I understand why you would think that. But don't forget, for a function to have a derivative, it must be differentiable, meaning the slope as I approach negative 1 must be equal to the slope as I approach negative 1 from both sides, or else we could have a cusp or a corner. If we've got a graph, and here's negative 1, and the slope as I approach negative 1 from the left is some number, and the slope as I approach negative 1 from the right is a different number, that's going to create it to be not differentiable. So we need to check for that first. Is the slope from the left and the right going to be equal? So let's first go ahead and find out, all right, what is f prime of x? Of the top function, it's 3. Of the bottom function, it's negative 2x. Therefore, what is f prime of negative 1? The top function, I can't plug in anything, so it's still 3. And when I plug in a negative 1 here, negative 2 times negative 1 is 2. Is the slope from the left and from the right equal to one another? No. Therefore, my function is not differentiable, and therefore it does not have a slope at negative 1. All right, it says, which of the following are true about f? As I approach 1 from the left-hand side, is that equal to when I approach 1 from the right-hand side? Well, I'm going to go ahead and plug in 1 to the top function and 1 to the bottom function. So I'm going to say f of 1 would be 3 times 1 minus 2. That gets me 1. Natural log of 3 times 1 minus 2. Ooh, that'd be the natural log of 1, which is 0. So as I approach 1 from the left and from the right, it did not equal one another. I don't like 1. Okay. How about the slopes as I approach 1 from the left and the right? I'm first just going to find f prime of x, not at 1. F prime of my top function is 3. The derivative of natural log of 3x minus 2 is 1 over 3x minus 2 times the derivative of 3x minus 2, which is 3. All right, let's go ahead and find out what f prime of 1 is then. Be 3 on top, be 1 over 3 times 1 minus 2 times 3, getting me 3 over 1, which is also 3. So it is, the limits are equal to each other from either side, which might make you think, oh, okay, then it's got to be differentiable if my slopes were the same. But here's the deal. Whoops, my slope's here. Here's the deal. Didn't we say, option 1, that as I approach 1, the functions, if it was discontinuous, as I approach 1 from the left, we got 1. As I approached 1 from the right, we got 0. So, okay, they both have a slope of 3, but they have a discontinuity, and therefore my function is not differentiable. Ooh, that's a tricky one. So only 2 is true. Again, because my function was discontinuous, I get that the slopes at 1 matched, but if we have a discontinuity, we cannot be differentiable at that point. All right, so we've got this function. Where is my function not continuous? Where is it not continuous? Let's think about things that make functions not continuous. If we've got vertical asymptotes, a function is not continuous. And if we have discontinuities, like a hole, my function is not continuous. So let's go see what we've got here. A hole is when you've got a common factor in the numerator and denominator. So we're going to have a hole at x is 2. Then a vertical asymptote is when the denominator is equal to 0. My denominator, once I remove the hole, is x plus 1. When will that equal 0? When my x is negative 1. So we've got two discontinuities, one at 2, one at negative 1. Answer D. If all we know is that the vertical line x equals 2 is a vertical asymptote, that's all we know, which of the following must be false? Okay, so I'm going to start with B here. As x approaches 2, as we approach 2, and they didn't specify from which side, so I'm going to say from both sides. As we approach 2, could my limit be negative infinity? Yes, I think it could. And they're looking for what could be false, so I disagree with B. As I look at C, as x approaches 2, could my limit be equal to positive infinity? Yes. Again, I'm okay with that. D says, as x approaches infinity, could my y value approach 2? Well, sure, if there was a horizontal asymptote, we don't know that there is, we don't know that there isn't, so I'm not ready to say that that must be false. And let's see if it's, the last one says, as x approaches infinity, could my y approach infinity? Sure. I don't have enough to say that it's not, so I'm not having any problem with E. Let's go back to A. As x approaches 2, they're saying the value of my function is 0. I got some big beef with that. My function does not exist at 2 because I've got a vertical asymptote. My slope is undefined. Nothing exists. So when x approaches 2, I cannot have a limit of 0. A has to be false. All right, on 89, it says the limit as x approaches a of a function is equal to the value of the function. So I'm going to say an arbitrary a here. And if I've got a function here, I'm going to say, here's my function. And would you agree the limit as I approach a from the left and a from the right, the limit does exist. And it says that it equals the value of the function, because I'm going to make that a nice, I'm going to make sure that that's not a hole. It's a nice filled in value, and I'll make it blue just to make that a little bit more clear. Okay, does my function have to be continuous? If the value of the function equals the limit, I would say yes. Ooh, and which one must be true? I'm like an A. Does it have to be differentiable? Oh, well, look what I did. I chose a cusp or a corner there just to be a little ornery. And that is not differentiable at A, but still fits this requirement that the limit equals the value of the function. So I do not like B. For all values, the function the f of x has to be equal to f of a. Well, in this case, let's say that I want to make my f of a, I don't know, 4. Does the function have to always be equal to 4? No, I disagree. That would be, in this case, if we had a horizontal line. Nope, not the case. Does not have to be true. The line y equals f of a is tangent to the graph of f of x. Again, if I have this cusp or corner, I can't even have a tangent line there. So I disagree with D. The line x equals a is a vertical asymptote. Oh no, if my limit exists, I'm not gonna have a vertical asymptote there, because then my limits would be negative infinity or infinity, not an actual value. Answer is A. 92 goes back to the extreme value theorem, that if a function is continuous on a closed interval, then it is guaranteed to have a maximum and a minimum. So if it does not attain a maximum or a minimum, that means that it has to not be continuous, because they gave us a closed interval, and the only way for it not to have a max or a minimum, so let's say I have this function. As long as it's not on a closed interval, so my endpoints are closed, then we have to have, in this case, I don't know, maybe this would be my minimum and that would be my maximum, as long as it's continuous. Because again, this is on a closed interval. Oh, this is on a closed interval, but we are not guaranteed maxes and mins. Like I have no maximum here because of this discontinuity. I don't know what I could call my maximum because it's discontinuous. So unless a function is continuous on a closed interval, we are not guaranteed maximums and minimums. Guys, the last part of this review is L'Hopital's, which I have not taught you yet, so we get to skip it.